All right, so to do a breakdown here, if we look at section 1.1, 1.1 was a crazy hodgepodge of all sorts of things. The big things to watch out for here is you're probably going to have to worry about a bunch of different definitions. So in other words, you want to make sure that if a term is used, like for example, if you have a question and the question says, hey, here's a graph, find an independent set of vertices. You need to know what independent set of vertices means. Okay? Some of the big things that we saw in section 1, we also looked at matchings. We looked at independent sets. We looked at halves. We looked at degrees of vertices. We looked at all sorts of different things. Okay, so this is mainly sort of looking at structures of graph and not really even going that far, but really more some of the big terms. Okay? In section 1.2, excuse me, we were way more focused. So this was where we looked at deciding whether two graphs were isomorphic or not. So you want to make sure that if you were given two graphs, you can tell or determine if they're isomorphic or not. So at the bare minimum, the answer is just yes or no. Yes, they're isomorphic. No, they're not isomorphic. But here's the expectation. If the two graphs are isomorphic, I would expect to see the isomorphism. Now, please note, there's not only, oh, is it not full? Let's try this. All right, I think, all right, hopefully that's better. All right, so if you find an isomorphism, no, that's the problem. Thank you. Haha, how's this? Better? Oh, good. Sorry about that, guys. That little window with the whiteboard there, that's just the intro so that you don't, so it doesn't look like you're in a crazy place when you log in when I'm not talking with you guys yet. It was under some other screens. I forgot it was up. Sorry about that. All right, so for isomorphic graphs, we're looking here at if there's a yes, you're looking for that function, that isomorphism. Note there's not only one answer. There may be several answers. If this was a fully paper test, either if we were together, if everything was in file upload like your homework, you guys could write whatever you want. If this is something where you need to input it into Canvas, you may have some things where you're either given part of the isomorphism or you have directions that says something like if you have more than one choice between who you're going to say match vertex 1 to, if it could be matched to either vertex A, B, or C, pick the one that's earlier in the alphabet, and that would be a way to make it so Canvas could grade these things. Okay? But I'll have all of that stuff in directions, so just make sure you read the directions if you run into an issue like that. If the answer is no, the two graphs are not isomorphic, you would need to explain why they're not isomorphic. Okay? Typically, based on the time frame, it's easier just to write down all of your work as you go through it. So like what we did in class, number of vertices, number of edges, degrees of everybody, and then you start dealing with either your subgraphs or your complement graphs or you're finding a circuit that looks distinctive or whatever it is that you do and go through those procedures. Okay? Note, if you've gone through like 5 different things and everything matches, definitely start thinking maybe this guy really is an isomorphism. In section 1.3, this is where we did our edge counting. So this is where you could be given a situation where you're told, hey, if we've got X number of vertices and we know this about them, like what their degrees are, how many edges are in the graph. Or if you know how many edges are in a graph, maybe you need to find how many vertices are in the graph. So we had several different examples dealing with that in section 1.3, and you had a couple of your Canvas quiz, one or two of them that dealt with that section 1.3 stuff in the past. Okay. The test is an online test. I'm currently looking into the different formats. So that has not fully been decided yet, but what is likely going to happen is you're going to have 2 parts. I mentioned this a little bit ago, where one of them would be something where you'd have to write out and do a file upload. and the other part would be something where you would type in your answers into Canvas. And then the last section that we covered in Chapter 1 was planar graphs. Technically, there is another section in Section 1.4, and that is Section 1.5, but 1.5 is just a bunch of extra questions, and what you'll see when we get to the second page of this study guide right here, which is the only page that was posted up on Canvas so far, is when it gives you some sample questions that you could work. They actually come from Section 1.5. And remember what we did with planar graphs. We looked at what? We looked at what a planar graph was, what a plane graph was, how to find the dual of graphs. This is where we defined what faces were and the degrees of faces. And one of the big things besides all those definitional stuff is make sure you're comfortable with Euler's formula. And the official way of writing Euler's formula is number of faces equals number of edges minus number of vertices plus 2. That's actually the specific instance in, I'm going to lie to you, but it gives you the right impression because we're so early in graph theory. It's the two-dimensional version of Euler's theorem. There actually is, when you get up to technically non-planar graphs, you have we call it an extended version of Euler's formula. So that's the stuff dealing with Chapter 1. So the question is, well, we need to know the proofs from that homework set. When you say that homework set, do you mean the Section 1.4 homework set? Okay. So in terms of proofs for this first test for the midterm, I typically don't ask people to do formal proofs. I might ask you to explain something. So similar to what we did yesterday on Section 1.4, where there was a question and it said, hey, we did a couple of them like it. What was one of them? One of them was said you do something and you're forced to always have triangular faces. And what did you have to do? You pulled out some of our formulas. We manipulated some of the formulas with some algebra and we said, hey, because we got this result, that really means we now got the result we were supposed to get, which is all the meat of a real proof. But since we haven't gone over how to do a formal proof with graphs, I'm not expecting that from you. The most I'll expect from you guys is if you can explain something. So that is, I would not consider that a proof. So the question was, if you're dealing with non-planar graphs, trying to find, I'm assuming you meant the K5 or the K33 configuration graph, subgraph? Okay, that is a possibility. Now, I don't normally ask you to go that far. Normally, I would just say, hey, determine whether this graph is planar or not planar, and then you can pick the way that you want to do it, or something like use the circle chord method to find that the graph is not planar. I could ask you to find a subgraph that is one of those configurations, but if I did, it would be a relatively small graph, and instead of being a configuration, it's typically just a subgraph that is one of those two complete graphs. And that is not because it's not an important thing to know, it's purely a timing sense. That way, this thing doesn't take you like 3 hours to do the test. So yes, in this section, it's not just knowing Euler's formula. You also have to make sure you can do things like find the dual and determine whether somebody's planar or not planar. Right here is just broad strokes. We'll get to more details on the next page. So 2.1 deals with Euler cycles, and we gave those definitions last time, and we'll start off today when we stop doing the study guide with talking about Euler cycles in just a second, or I guess a couple minutes. And section 2.2 is dealing with something called Hamilton circuits. And so that'll be, based on the current time, that'll be what we'll look at the latter half of today. So let's get into the specifics, and then we'll make sure to get more examples of these guys from Chapter 2 when we finish talking about the study guide. I'm going to scroll. So that's just all the scratch work. I left myself space so I could do scratch work on the same page. Okay. So this here is what you guys would have had so far. Okay? So tells you which sections. This one here didn't do chapter, it actually lists out the sections. Same date we said. Basic terms and items. I went ahead and split this out of saying section 1 because in your book we actually pulled stuff that wasn't only in section 1. So you want to make sure that you recognize the different types of graphs, your simple graphs, what's a multi-graph, a bipartite graph, a directed graph. Did we have anything else? Oh, we had the directed multi-graph. So if somebody says, hey, do such and such on a multi-graph, you want to make sure you're comfortable with what a multi-graph is. Make sure you're comfortable with components of graphs, or really I should say parts of graphs because component is a buzzword. So things like their paths and our trails and our walks, doing it where you start and stop at the same place, whether the graph's connected or disconnected, what's a component of a graph, what's a subgraph. Okay? Again, it might be things that you need to find, or it might just be one of the terms used in the question. Properties that are related to vertices. So make sure you can handle adjacent vertices, a vertex incident to an edge. Remember, adjacent is where you can get to the other vertex via an edge. Incident is where they're actually touching. Degree of a vertex, edge covers, independent sets, vertex basis. And then things that are related to edges. You can also do incident. So edges can be incident if they share a common endpoint. They can be incident to a vertex. And the big things that we talked about were bridges and cut sets. And remember, bridges and cut sets were the edges that you'd remove from a graph to make the graph go from whatever it currently is into more disconnected, if it already is disconnected, and going from connected to disconnected if it's currently connected. And then dealing with faces, or as your book calls them, regions, you've got what a face is and also the degree of a face. And then the thing that you guys are starting to allude to is the details in each of the sections. So I did this for all the sections except for 1.1. With isomorphisms or section 1.2, the key things here are make sure you can figure out if they're isomorphic or not. We also talked, though, here about subgraphs. We talked about complete graphs. Actually, we talked about it a little bit ahead, but your book defines it here. Complement graphs, in degree, out degree. We actually talked about those up here. Isolated vertices or vertices that are not incident to any edge. So those things could happen, but since we didn't explicitly talk about that descriptor, you probably won't see that buzzword. And here, I went ahead and pulled out, instead of saying just go over all the homework we've ever talked about and all the examples we've ever talked about, sort of a quintessential example in this particular section if you pull exercise 5 from that section. And I did that same thing of these key exercises for each of the sections. So in section 1.3 with edge counting, the big formulas are degree sum equals twice the number of edges, and there was that corollary that went with it. We also looked at how components of a graph relate to connected graphs. We looked at determining if a graph was bipartite. This was the one where it wasn't just being able to draw the graph so that all the vertices were in 2 rows or 2 columns. This was where you looked at those circuits, and the circuits need to have an even number of edges in them, or an even length. Planar graphs, and this is actually the questions you guys were asking. Figuring out, knowing the difference between a planar graph and a plane graph, and what a dual graph is, knowing your circle chord method. So specifically here, this is determining if a graph is planar. I'm going kind of quickly here because we actually mentioned this stuff when I was just handwriting. Looking at the configurations, and then we had the 2 new formulas here, your degree sum of your faces, which we gave that formula as an F for face, and the inequality that dealt with if you were a connected planar graph. And then into the chapter 2 guys. So chapter 2 guys, this one here is being able to figure out if you actually have an Euler cycle or trail, and we actually talked about those guys last time, and then being able to show that none of them exist. And remember our theorem, we talked about these guys last time. In order to have your Euler cycle or trail, you had to look for your degrees on your vertices. Specifically, you need all those degrees to be even. And then here's a quintessential example. Now, Hamilton paths and circuits, this is what we're going to talk about today. So in terms of things that you need to know what they are, you need to be able to find one of them and actually be able to figure out, all right, well, would one of these Hamilton guys actually exist in a graph or not? So notice it's definitely mimicking what you would do with the Euler Trails or cycles. And they actually are often taught hand in hand because they are very, very similar. Okay. And then at the end, I went ahead and just did some extra stuff if you want extra practice questions, things to look at. Formatting-wise, I've tried to do all of our assignments, both the ones that I haven't figured out how to convert them online, as well as the assignments, quizzes, and homework that have been converted online, so that you could see how these different topics could be written if they were fully online, as opposed to just a file upload. Okay? So there's all sorts of things to look at. Now, before we go into the actual math topics today, any questions from you guys? And remember, if you do come up with any questions, either with respect to topics or otherwise, we'll totally talk about this stuff again on Monday. So one of the plans for Monday is if you guys run into any questions or problems or exercises that you were working over the weekend and you just got stuck or wanted to go over it together, we totally can do that on Monday. And also on Monday, I have to have definitive answers for you on all the details of the actual, what you will see day of in terms of the exam on Tuesday. I think I have solutions for at least some of those supplementary examples. Let me look for them. I'm not going to lie, with that many of them, I'm probably not, if I don't have them already somewhere, which I think I do, I'm probably not going to be able to get all of those answers back to you. Now, good news is if you look in the back of your textbook, your author is not awesome in terms of always giving you answers, but he does give you some hints and answers for at least some of those questions. Did I actually pick all the ones that he would do in the back? Nope, but at least some of those are ones that he would have done in the back of the book. Other questions from you guys before we jump into the Chapter 2 examples? Okay, well, in that case, what I will do is I'll go ahead and save a copy of this study guide with all of the new handwritten marks on it, and I'll go ahead and upload that to Canvas so you guys can see this too, even if you didn't note any of these changes. Note, most of the stuff we said was just reiterating the stuff that was already typed in here, but I'll go ahead and put this annotated version up there for you guys. All right. I got to do this in the right order so things don't go crazy on us. But in that case, let us go ahead and look at some more examples of the Euler cycles and trails. So remember the key thing here, and even if you totally don't even bother to remember the second half of the name, the cycle or the trail, the key thing to remember here is this Euler. So in terms of Euler cycles and trails, what you're looking at is you're looking at either a cycle or a trail, that visits every single edge in your graph. The key thing here is you're trying to travel across every single edge in your graph. Now, both a cycle and a trail do not allow you to cross the same edge more than once. So this is literally you're trying to visit every edge in your graph exactly once. For both of these two guys, it's almost automatic that you're going to have to visit a vertex. Well, you'll automatically visit all the vertices at least once, but you'll almost for sure have at least one vertex in your graph that you'll just have to visit more than once, unless you have a specialized graph. There are a couple of graphs that doesn't happen. All right, we looked at the quintessential example last time, but the main result here is this theorem 1 that says if you have a multigraph, this guy is going to have an Euler cycle if and only if, or exactly when, or this is the condition of when you can tell if the Euler cycle exists, if first the graph is connected, and we talked about why that was true last time, because if the graph wasn't connected, there's no way that you could actually reach all your edges. Okay? And second, if all of your vertices have even degree. And we ended before we got to this example right here. So this example kind of looks like an unfolded dice. It's got those 5 little box type shapes in sort of a, I don't know. Trying to think of a good descriptor there. I'm drawing a blank. Then it's got this triangle over here. Now that I'm looking at it more, it totally looks like a cartoon that's sort of blowing a horn, although that's probably just me. So what we want to do is we want to see if we can find an Euler cycle. But before we start doing that, what do you guys think? Does it look like an Euler cycle should exist? What do you guys think? All right, so we got a couple of votes for yes. Now, how would we determine that? And that's exactly as somebody else just wrote in. Yeah, if you look at all of these vertices, every single one of the vertices in this graph looks like it has either degree 2 or degree 4. So that means it has all even degrees, which means, yes, this guy better have an Euler cycle. Now, that means in terms of this particular question, the only thing we now actually have to do is, well, find that Euler cycle. Okay? So I have found, and you don't have to do this, but I have found it is easiest for me if, actually let me get the one that's a little bit more fat. I find it's easiest if I actually draw on the graph. So for example, if we're trying to find a cycle or trail, in this case, I would say, you know what, let's pick a vertex. You can pick any one you want because we're going to end up going to all of them. Well, we're going to visit all the edges anyway, and all the vertices are adjacent or incident to some edge. So maybe we start at A. I think orange is too close to red, so let us pick a different color here. How about yellow? So maybe we start here at A. Well, if we start at A and we're trying to do an Euler cycle, remember the two criteria. First criteria is, I guess you could say 3. First thing is we're going to want to travel across all the edges exactly once. And then we're going to come back to the starting point. Multigraphs, simple graphs are technically a subset of multigraphs. So a multigraph, you typically don't call somebody a multigraph until you've got the multi-edge. So you've got a pair of vertices that has 2 edges, using them as endpoints. But technically speaking, all simple graphs are actually a subset of your multigraphs. So anytime you have a theorem that talks about a multigraph, it automatically applies to simple graphs too. That's one of the nice things about having something that talks about multigraphs. It's way more applicable than a theorem that just applies to simple graphs. So if we start at A, where would you guys like to go to next? We can go to either B or D. Sure. So maybe you go to B next. Now, if you go to B next, that's totally fine. But now we're forced, we have to go to E. If we go to E next, we're going to come down there. And then we have 3 choices. We can go to F, we can go to K, or we could go to D. I'm going to try to be a little bit strategic about this, so I'm going to go ahead and force us to go over to F. But you could have gone one of those other 2 places too. Now, once you're at F, we're back and we're at a degree 2 vertex, so we are forced to go into only one direction. We have to go down to H. Now, here's where we're at another degree 4 vertex, but it's critical. But looking at the structure of the graph, I'm going to claim we only have 2 choices of where we can go if we actually want to get an Euler cycle. Anybody have a guess what those 2 choices are? Right. We only want to go out to either G or M in order to get the Euler cycle, because if you don't, if you go to L, what happens? You can't travel an edge more than once. So if we went down here to L, we'd never be able to get back to the edges in this triangular shape. So we have to either go to G or to M. It doesn't matter which. Do you guys have a preference? Sure. Now you're at M, you have to go to G, and wow, my hand definitely did not go in the right way there. I was trying to get way closer to the edges. It did not work. So go to M first, then go up to G, and let me put a little arrow here just to indicate which way we went. And then we came back to L, because once we got back to H, there was only one edge incident to vertex H that we hadn't used yet. Now, once we're at L, we used one of the edges coming into L, so we have to use the other edge going out to K. And once we are at K, then we have a decision. We can either go up to E or back to P, but right now we've been actually traveling along the outside of this graph. Let's keep doing it. No. So the question is an Euler cycle the same thing as an Euler trail? And the answer here is no. The Euler cycle has to start and stop at the same place. The Euler trail is the distinction where you couldn't get back to your starting point. And we're actually going to talk about that. That's what we're going to talk about right after we finish this example. So at K, I'm going to go ahead and pull us down to vertex P. Notice vertex P is degree 2. So you're forced to go to N. Vertex N is also degree 2. So we are forced to go up to J. Now at J, we're again degree 4. So we have 3 options of where we could be. And attempting to look ahead at all of them, I think it doesn't matter which one we take. So where would you guys like to go after J? I heard I, yes. So if we go to I, once we're at I, we're degree 2, so we have to go to C. Once we're at C, we're still degree 2, so we have to go to D. Now, big question. At D, where should we go next? Sure, we can continue going to E. The only thing you can't do is you can't go to A. And yes, we could have gone to J as well. Now, once we're at E, you're forced. Where do we have to go next? Only one option. We'll go down to K. Now, even though E was degree 4, we were still forced to go down to vertex K because we'd already traveled along 3 out of those 4 edges. So you could only go out the one that you hadn't traveled on before. Same thing happens at K. So now we're forced to go back to J. It's the only edge we haven't traveled on yet. And once we are on J, same thing happens. We are forced to go back to D. Now, once we're at D, remember, we're trying to get an Euler cycle, so we want to end up eventually at the vertex A. Can we actually do that here? We're supposed to be able to according to that theorem 1. Yep, don't overthink it. Once we get to D, just follow that one edge that we haven't covered yet, and we will get back to A. Now, it should be the exact same length as the length of however many edges were in this graph. I hadn't counted them. So we're going to assume you're right. Yeah, so it is not a short cycle. So if we actually wrote this out, which I really don't want to do, we'd say what? We go A to B to E, went then F, then H, then M, then G, then back to H, then to L, then to K, then to P, N, J, I, C, D, E, K, J, D, and finally back to A. And please note, while it's definitely easier to determine your cycler path by writing and scribbling on the graph itself, unless you put in those little arrows and clearly indicate where you start or stop, anybody else reading your scratch work does not know what you are saying. Okay? So that would be an example of finding an Euler cycle. Notice we used every single vertex in the graph, not vertex, we used every single edge in the graph exactly once, but some of those vertices we actually ended up having to visit more than once, and every vertex that had a degree larger than 2 had to be visited more than once. You can actually tell how many times you're going to visit the vertex by, as long as it's not your starting vertex, by taking the degree of the vertex and dividing by 2. So for example, notice vertex F was degree 2. We traveled through vertex F essentially once in, once out. So if we were walking, we walked through it once. Whereas vertex E, we visited it twice. Once when we came down B to E to F, and once when we went D, E, K. Notice degree 4 divided by 2, it's 2. We visited it twice. If that helps. The other one is just color coding which edge you used. Questions? Make sense? Feeling kind of okay so far? All right, I am not seeing anybody scramble with questions. So if you got ones, definitely shout out, but let's move on to the next thing. So the next thing is actually a corollary, and it's a corollary of this theorem 1. So theorem 1 says you've got this graph. The only thing that's stipulated with the graph is you're not allowed to have directed edges. It's going to have this Euler cycle exactly when you're both connected and all your vertices have degrees that are even. So the corollary is using that same information, but now we're jumping from an Euler cycle to an Euler trail. And let me go ahead and highlight this guy. So this one here, we're looking at actually I don't want to highlight it that obnoxiously. We're looking at an Euler trail. Now remember, in terms of the Euler trail, the difference between the trail and the cycle is the trail is not going to end at the same vertex where you started. Okay? So here, you're only going to get the Euler trail, which still has to visit all the edges if you're still a connected graph, but now all of your vertices still have even degree except for 2 of them. These 2 vertices, which have odd degree, those guys are going to be where you start and stop. So those guys are going to be where the trail begins and also where the trail would end. Now, in terms of, just a second, try to do something it didn't take. In terms of figuring out which is which, it doesn't matter. Your trail could start at one of them or start at the other one, your choice. Oops. All right, so suppose we have this little baby graph example right here. And I on purpose did a smaller one. So if we look at this little baby graph example, first question is, do you think it has an Euler cycle? And while you guys are thinking about that, I'm going to change my pen color. All right, so we've got 1 vote. What do you guys think? Is he right? All right, so for the Euler cycle, there is no Euler cycle here. Now, why? What makes you guys sure there's no Euler cycle here? So this would be if you were asked to explain your answer, what would be our reason? Yeah, we've got some odd degrees in here. I'm going to go ahead and write out and say, hey, you know what? Degree A, the degree of vertex A is 3. Okay? Now, if we then look for an Euler trail, what do you guys think? I did not mean to write the word trail yet. What is it? Euler trail. So for an Euler trail, what do you think? Can we get an Euler trail? We can't get the cycle, but could we get the trail? This one, yes. Why? Because we have exactly 2 vertices that have degree 3, so those are our 2 odd vertices, and everybody else has an even degree. So this one we should be able to get. So let's find it. And let me go ahead and get something that is a little bit easier to see. Maybe purplish would work. So you have to start with one of the 2 odd degrees, so vertices with odd degree. So we either have to start at A or at C. Which do you guys want to do? Do you want to start at A or C? Hint, it doesn't matter. Okay? So if we start at A, then we have to go somewhere. Where would you guys like to go next? Our choices are B, C, or D. In other words, we have many choices. I've got 1 vote for C. Anybody else have a preference? I'm seeing no other votes, so let's go to C. I'm going to put an arrow there to indicate that that's the first place we went. So once we go to C, now we have a choice. We can go either to B or to D. Do you guys have a preference? And it's not going to matter. Okay? So here, we'll go to D. Once you're at D, you're forced to go back to A. Once you're at A, you're forced to go to B. And then we end up at C. And yeah, I know I've moved around a vertices that looks really stupid in retrospect. I was just trying to make it so it was easy to see what the actual trail is. So here we started at A, then we went to C, then we went to D, back to A, through B, and we ended at C. Notice A was one of our degree 3 vertices, and C was the other degree 3 vertex. And note, a trail cannot go over the same twice, just like the Euler cycle couldn't. It did visit all of the edges exactly once, just like the Euler cycle did. The only difference here is your start and your end vertex are different now. And they will 100% be your 2 odd degree vertices. Okay? Questions? Make sense? Kind of feeling okay-ish. That's literally it in terms of the Euler cycles and trails. All right, I am seeing no questions from you guys, so next question. So the next questions that I've got, and this one I actually went ahead and put in as a question thrown to you guys to the poll everywhere, so I'll go ahead and share this with you. It is the exact same question. The question here is, if you have a graph that's connected and you know it has an Euler cycle, so we're actually right now talking about cycles as opposed to the trails we just talked about, although you could ask the same question about trails, and we will actually in just a second. If it's an Euler cycle, do you think that that graph can also have a bridge? Now the key thing here is to remember what a bridge is in a graph. So, quick shout out, do you guys remember what a bridge is of a graph? Would it be helpful if I drew a picture of a graph that had a bridge in it? Oh, I like how all of your answers came in almost at once on my end. Yes, so the definition of a bridge is a single edge that if you remove that single edge, the graph transforms from a connected graph into a disconnected graph. So I'm going to go ahead and draw a picture of that while you guys are deciding or determining whether you think an Euler cycle could actually exist in a, if a graph with an Euler cycle could ever have a bridge in it. So this here is an example of a graph with a bridge. Oh, and I'll make it a crazy example just because. Mainly because I don't normally make crazy examples. So the bridge is the edge AB. And I'm not saying that's an awesome example, especially not an awesome example for if you're trying to have an Euler cycle. But it does show you where the bridge is. The bridge is the AB edge. All right, it looks like most of you have a guess now, so I'm going to go ahead and hide this second screen so I don't forget. Let's not have that mistake twice today. All right, so in terms of these guys, think about where you can start if you wanted to start your Euler cycle. Now, you're supposed to be able to have an Euler cycle, right? So that means we better be able to start it here. It's still active, so go ahead. If you didn't answer it, you can go ahead and answer a question there too. So if you go ahead and you try to look to see if you have an Euler cycle. Now this one here obviously does not have an Euler cycle. And why would I say this example is potentially a bad example for trying to find an Euler cycle? Because it obviously doesn't have one, and it's not because of the bridge. Any guesses in terms? Yeah, it's the odd degrees. And we have odd degrees all over the place. There's an odd degree there, there's an odd degree there, there's an odd degree there. Oh, that one's actually even. Odd degree, odd degree, odd degree. So lots of odd degrees. And there's so many odd degrees we can't even get an Euler trail. But suppose I didn't put in the edges where you got all these odd degrees. Okay? But suppose we had this bridge in there still. So in this situation, if we're trying to look for your Euler cycle, trying to get a different color here. Suppose the cycle starts somewhere. Well, you're eventually with your cycle going to reach all of your edges and all of your vertices if it exists. And we're assuming that we have one. Well, what happens? Well, if you start, say, over here because I'm lazy, the Euler cycle would do what? It would go around all of the edges in here, whatever was actually on this side of the graph, probably not this pentagonal shape. Okay? And then at some point, what would have to happen? When it travels across all or at least some of these edges, it would have to eventually go where? It would eventually have to use which edge? It would eventually have to use that bridge edge. So you do whatever you do over here, stuff, and then you'd have to use that bridge edge. And then over here, you try to get an Euler cycle over here. So at B, you go around and try to visit all of your edges. And notice here, obviously, it's not going to happen in this example because I was just apparently having fun with vertices and edges when I drew it. But if we actually had the right number of right degrees in all of our vertices here, you'd actually have like a mini little Euler cycle where you'd start at B and come back to B. But once you came back to B, so you went around and did all of your little things in here and you came back to B, what's the problem? You started over here at, let's call it X. You've reached at least some of the edges here. You crossed over on the bridge. You got your Euler cycle, your mini Euler cycle over here. But now, yeah, the only way to get back to A is you'd have to cross that bridge again, and you're not allowed to reuse the edges exactly. So the issue here is if you actually, and here's the conclusion, if there really is an Euler cycle, so if there's an Euler cycle, the minimum cut set you have, and remember, a bridge is actually a cut set that has exactly one edge in it. Okay? The minimum cut set must have at least 2 edges in it. And why would I say at least 2 edges? Because that allows you to go there and then come back with the 2 big parts of the graph. Okay? And if your minimum cut set has at least 2 edges, that means by your definition of what a bridge is, there is no bridge in the graph. Okay? Now, suppose we ask this exact same question, but replace the buzzword cycle with the word trail. What do you guys think? You think it could be possible to get an Euler trail in a graph that has a bridge? Yeah, so that one actually turns out to be perfectly possible. You do your stuff over here on one side, you cross to the, or actually let me follow the arrows. You start on one side, you get all the edges, then you cross over on the bridge and you do all of your stuff, then there's no need then to go back because it's a trail, not a cycle. You don't have to get back to your starting point. It's like moving as opposed to visiting somebody. But that is the last example I've got for us in section 2.1. That actually takes care of everything that we care about with the Euler cycles and trails. Yes, so let me go ahead and draw that example. You mean something like this. Are you thinking of that as the entirety of the graph? Then yeah, that guy would that one edge would be considered a bridge, and also the Euler trail would simply be start at whichever endpoint you want, cross over to the other endpoint, bam, you're good, you've got the Euler trail. Both of these have degree 1, so there's exactly 2 vertices with an odd degree. So yeah, that would work just fine. And note also an Euler cycle doesn't work because there is no cycle whatsoever in this graph, regardless of Euler or otherwise. Okay. So other questions with the Euler guys before we move on to our other types of actually circuits and paths for the other one. All right, so the big takeaway is for the guys tagged Euler in front of their name, you're trying to reach every single edge in the graph. Repeat vertices, don't repeat vertices, we don't care, but reach every edge exactly once, and the degree of your vertices is going to matter. You want even degrees, except in a trail where there's exactly 2 that have odd degrees. We're now going to switch over to something else. So the other thing that we've got, and these guys are typically given right in the same line with your Euler cycles and trails, are Hamilton circuits and paths. Now, fair warning, your book calls these guys Hamilton circuits and paths. The path part, everybody calls it a path, but a lot of people also call these guys Hamiltonian circuits and paths. So if you see either Hamilton or Hamiltonian, if you're looking things up, it's the exact same thing. So these guys here are, when you're dealing with them, they're very, very similar to the Euler cycles and trails, but the key difference is instead of caring about your edges, we don't anymore. Now all we care about is we want to reach every vertex in the graph, and here is we want to reach them exactly once, okay? So the extra thing that is not said here, although it is included in the definition of your circuits and paths, is we want to reach every vertex of the graph exactly once. So that's the key thing there. Now, if we wanted to go ahead and look at an example of this guy, I went ahead and prepped up an example of a graph that's actually the same graph that we looked at just a second ago. And here's what we know about this graph. This graph of 4 vertices and 5 edges, it does not, so no Euler cycle, because it had the 2°3 vertices. It did have an Euler trail, so has Euler Trail. But let's see what's going on in terms of the Hamilton circuits and paths. So if you look at this guy, this graph, what do you guys think? Could we actually form a circuit that reaches all of those vertices? Does not have to reach all the edges, it just has to reach all the vertices. Yep. Now, where would you guys like to start for this circuit? Anybody have a preference? I have to admit, I'm going to go with D. I don't normally get that one. So, once you have got whatever vertex you want to start with, and it doesn't matter which one you start with, where do you go next? Well, somebody that's adjacent to your current vertex. So if we actually started with D here, where do you guys want to go next? I saw A the most, so we'll go at A next. Once you're at A, you have to go to B because A is degree 2. And once you're at B, well, if you went back to D, you close the circuit and you're done. So we're going to go to C. Once we're at C, we'll come back to D. Or if you're super lazy, like what I was going to do if you guys didn't give me examples, is you could also do the circuit A, B, C, D, and back to A. So in this case, we just went around the outside, but you could you have done this one? Let's see, one. Could not have gone through the middle. You would have actually hampered yourself. Now, any guesses if we could find a Hamilton in this graph? Now, don't overthink this. Oh, that is A1. And there's the easiest one. If you want to be as lazy as humanly possible, you can grab any Hamilton circuit that you have and just delete off that last edge where you went back to your starting point. Okay? You can also do a bunch of other things. You can also do one of the ones that you guys sent in, which was, I'm popping it, C to B to D to A. So this one sort of looks like a Z shape or an S shape. And what happens there, that's also a Hamilton path. Now notice the two distinctions between those two different Hamilton paths, which is why I wrote them both. One of them was just a Hamilton circuit, and you removed one of the edges to make it a path. Actually, the last edge to make it a path. But the other one, this one that starts at C and goes to A at the bottom there, that one, there's no way to make that swittle into a Hamilton circuit. There are definitely cases where you do not have a Hamilton circuit in path, but you are still able to that reaches all of the vertices. All right, so that's one example. Let us look at another example. Now, the key things to remember are the Euler cycles and trails deal with the edges. You have to get to all the edges exactly once. The Hamilton circuits and paths, that's where you reach all the vertices exactly once. Now, suppose you get this graph here, which we've looked at before in the past. It's one that kind of looks like a bow tie here. What do you guys think? Can we get an Euler cycle or trail? Could we get a Hamilton circuit or path? And let's start off with the Euler ones. Did we look at this one when we were dealing with Euler cycles? I think we may have. So what do you guys think? Does this guy have an Euler cycle? Yeah, and even if you're not spotting what it is, notice the degrees of all but one of the vertices are 2, and the middle degree is 4. So there's all even degrees, which tells you have a Euler cycle. It also tells you that there is no Euler trail because there's no pair of vertices that have odd degree. So notice just by looking at the degrees of your vertices, you can tell immediately if there's a cycle or a trail. So with this Euler cycle, anybody spot one? Well, let me rephrase. Where would you guys like to start for us to find an Euler trail? Oh, there's one. So if we start at A, we can go to either E or B. It doesn't matter. So we could go then here to, I want to draw on here the one for the Hamilton ones because that's what we're now talking about. So I'm just going to very lightly indicate where we're at. So A to B, then you can go at B, either up to C or down to D, it doesn't matter which. You can either cross or go back up. If you go around the outside of this guy, you could go A to B to C, then down to D. But once you're at D, you're forced back to B. And once you're at B, you're forced to E, and then you go back to A. But it works just fine. Now, when we get into the Hamilton guys, what do you think? I think a Hamilton circuit might exist here. Remember, a circuit, you need to start and stop at the same place. You don't repeat edges, and you want to reach all of your vertices. And you can't repeat vertices. So I got a couple of votes for no here, and that's totally correct. What happens if you try to start at either A, E, C, or D, you get a cycle that looks very, very similar to the Euler cycle. What happens? You have to cross through vertex B twice. Exactly. But if you try to start at B and try to circumvent that, what happens? You start at B, you go around, and you get back to B, and all of a sudden your circuit cuts off. A circuit ends exactly when you reach your starting vertex the second time. So you go around and bam, all of a sudden you didn't get to the other side. So nope, it turned out there is no Hamilton circuit in this graph. And this is something that happens frequently, where you do have the Euler cycle, but you don't have the Hamilton circuit, or vice versa. Now, last one, what if we looked at the Hamilton path? What do you guys think? Do you think a Hamilton path might exist? All right, we got several yeses for the path, so let's find one. Suppose we start at A because that's where we did with the other one. And then we have to decide whether we go to either B or E. And it turns out it's going to matter which one we go to. Right, you want to go down to E. Now, once you go to E, you're forced. It's degree 2, you have to go to B. Now, once you're at B, where do we want to go after B? Could. So we could go to D. And once we're at D, we're forced. We're going to actually go up here to C. So if we write this out, this would be A to E to B, D back to C. And the only real thing that could change there if you start at vertex A is you could have visited C first and then come back to D. Huh. Makes sense? Kind of feeling okay a little bit. Now notice finding your Euler cycles and trails, now that we know about that degree thing, well, actually finding them takes a little work. Knowing that they exist is pretty straightforward from that theorem of the previous section. Hamilton's circuits and paths, we don't have one of those really quick theorems yet. So actually finding them in the graph, you actually have to search for things. You got to see, all right, how would I get to each of the vertices exactly once? And then the only difference is whether you come back to your starting point or not. It's definitely easier to find the Hamilton path because you don't have to worry about coming back to where you started. So let us look at a slightly more complicated graph. Oh, I guess I left the space so I could throw that writing out below the picture. Suppose we are looking at something like this. So in terms of, if you're trying to draw it out for yourself right now, here's what this thing is supposed to look like, slightly off scale. It looks like a big pentagon. So 5 vertices around the outside and edges between all 5 of those vertices. And then on the inside, it almost looks like a tiny pentagon, except the edges aren't drawn in correctly for that. You've got this star-shaped where there's a vertex in the very, very center, and it goes out in 5 positions. And if you actually see this graph computer generated instead of hand-drawn, the vertices that are the F, G, H, I, and J actually form a straight line with vertex K and their outer vertices. So F here lines up fine, but G really should have been moved a little bit to line up K, G, then B. That was actually pretty decent. I is okay. J is a little off too. Okay. Now, in terms of connecting between the outer pentagon and the inner star-shaped here, what happens? At vertex A, we did not connect directly to the vertex that looks like it corresponds on the inner level. Vertex A is connected to the 2 on either side of the vertex that looks like it corresponds. So A is connected to J and G. Same deal with B. B is connected to F and H. Same thing with C. C is connected to G and I. D is connected to H and J. And finally, E is connected with F and I. Okay. So it's essentially, it's like 2 levels. Okay. It would not, configuration, let's see. So if you removed vertex K and the 5 vertices incident to it, and for these vertices F, G, H, I, J, those guys, they sort of got absorbed into the line here, then yeah, it would kind of look, it would be a K5 configuration there. So what does that tell you? That tells you just identified a K5 configuration. So even though we didn't ask it, that would mean that this graph would be a non-planar graph. Because you have a K5 configuration that is a subgraph. Because it's everything that's not dealing with K. All right, so what we actually care about. So the question here is we are going to figure out if we have a Hamilton circuit in this graph or not, or we're going to attempt to. So one of the things that you would want to do is you want to look at maybe some of the key markers. So if you look at this, and when you look at the properties of it, or you look at structurally what this graph currently looks like, it definitely looks what's known as symmetric. In other words, if you rotated this graph, it doesn't matter if CD looks like it's on the bottom, or ED looks like it's on the bottom, or AE looks like it's on the bottom. If you rotate it, it's still the exact same picture. If you did the mirror image of it, so if you flip-flopped it, it'd still be the same picture. Okay? So that's a nice thing. That means if you do something that looks like it works in this piece, you can copy that as you go around the graph. Now, that doesn't always work perfectly, and in fact, this time it's not going to work 100% perfectly, but it's going to be close to helping us. The other thing is some things that you can always do at the beginning. You can always say, hey, how many vertices do we have? In this case, there should be 11. 5 on the outside, 5 on the inside, and then K. If you want to count up the edges, you can. I really don't, so let's not count the number of edges right now. But what this tells us is we can actually do some preliminary stuff, and we can look at our Euler cycles. And I'm just going to abbreviate Euler cycles. So what do you guys think? Do you think there might be an Euler cycle in this guy? And I realize that's not the question. This is putting in a little extra. So what do you think? Does it look like there might be an Euler cycle in this graph? Got one vote for no. What do you guys think? Is there no Euler cycle in this graph? Yeah, so there's no Euler cycle in this graph, and that's because you can find the vertex. I'm going to pick on vertex F because it was the first one I saw that has an odd degree. Now, as soon as you spot a vertex with odd degree, you ask yourself, hey, maybe there's an Euler trail. So I'm going to abbreviate Euler Trail again. So what do you think? Does it look like there might be an Euler trail here? Remember, with Euler Trail, you have to have exactly 2 vertices that have degree. That's an odd degree. And correct, here we have more than 2. We have how many? We've got 1, 2, 3, 4, 5 of them. And actually, K has odd degree too. It's just not degree 3, it's degree 5. So we actually have 6 vertices with odd degree. That's also a no. But now let's actually get to a Hamilton circuit. Full disclosure, finding a Hamilton circuit in a graph, it is typically easiest to just start doing it. So let me go ahead and highlight what we're doing. Oh, let's actually properly highlight. We can do it that way. So suppose we start at A. It really doesn't matter which vertex you start with, but since you guys normally pick A and I like picking A and it's at the top of the vertex, let's start with A. Now, it does actually depend on what you do. One of the things that I know that I have a tendency to really want to do is I would really want to go all the way around the outside of the graph and then come in on the inside of the graph. Except the way this graph is structured, that's not going to work. Okay? If you go all the way around the graph, that's fine, but as soon as you come inside the graph, you have to go down to K, and then the only place is to go out, and then once you're here, at this stage, you have to go to the outside of the graph again, and we've already dealt with those vertices. In Hamilton circuits, you can only visit the vertex once. So, can't do that strategy. So instead, notice the inside structure of this graph. The inside structure of the graph is a star shape, and the connections between the inside star shape and the outside pentagonal shape, or this circuit on the outside, is very much the inside bits. Here, you can't get around them very easily. But each one of these vertices is connected to 2 vertices on the outside. Now, what this means structurally, if we don't want to draw a bunch of different starts of Hamilton circuits and then get stuck, is we're going to need to go from the outside level vertices to the inside level vertices and back and forth. Okay? So, first one is, I'm going to go ahead and take us into G. Just go ahead and go straight into G. Now, once we're at G, we could actually go into K if we wanted to, but I'm going to go ahead and just take us all the way back to the outside. Now, once we're at the outside of the graph, we could go in a couple different places. We could go back to the inside. We could go to D. We could go to B. But since we've actually already looked at the vertices A, G, and C, just so I don't accidentally forget a vertex in the future, I'm going to go back and pick up vertex B. Now, once we're at vertex B, we actually can't get to anybody on the outside level. So we can't reach D or E immediately, but we can go back to the inside. And if we go back to the inside, we could go to either H or F, but the way I sort of hooked this right here, I'm just going to go to F. That way the line doesn't look weird and squiggly for you guys. Now, once we're at F, we could actually do the same thing. What? Apparently my arm got on the keypad. All right, so once we're at F, I'm just going to go ahead and take us all the way over to E. Now, once we're at E, notice we could go either to D or we could go to, where's the other one? Or we could go to I. Now watch out, this is where you can start running into trouble, okay? If we go to D and then try to muck around inside, notice we'll have 4 vertices on the inside, and D, H, K, I, well that works out, but then we'd have to get kicked back to the outside. So that's not going to help us yet. We're going to want to instead go inside right now. One of the ways when you get about halfway through your Euler circuit when you're trying to build it is sometimes it's nice to start at back where you're supposed to end and backtrack. So for example, since we just used E, notice the second to last vertex in this cycle is going to have to be J. So somehow we're going to have to come out to J. Sometimes that helps. So here, I'm going to go ahead and from E, I'm going to go inside the circle, or to the center of the graph, and go to I. Now at I, we actually are forced to go where? Because I is degree 3, we've used one of the edges. Technically there's 2 edges, but you have to go into K because we've already visited C. Now once you're at C, remember how we talked about J need to be the second to last guy? That means we need to come down to H. And once you're at H, you're forced to go to D. And once you're at D, you're forced to go to J. And once you're at J, you're forced to go back to A. Now put the little arrows there so we knew which edge to take out of A and which edge came back into A. Okay? So that would be an example of a Hamilton circuit. And if we actually wrote this guy out, we were A, G, C, B, F, E, should I get the right one? I, K, H, D, J, and A. No, that's not the only one. There are other ways to do it, but they would have a similar structure where you'd have to be on the outermost ring of vertices, then you're coming into the innermost ring of vertices. Maybe you pick up a couple of them sequentially from the outer ring like we did C to B. Maybe you pick up a couple of them sequentially inside in the inner star-shaped like we did I, K to H. Okay? But you'd have to do that pattern of in and out. Questions make sense? Kind of feeling okay a little bit. Ooh, I like that. That was fun. All right, so in terms of what we just did, what we talked through, and I probably didn't talk through awesomely, but what we had to think strategically when we were picking that path that created eventually really a circuit was that where were we going next? What did we have to worry about? What edges were already used? What vertices were already used? Somebody actually put that into 3 rules to keep track of. Okay? So here are the 3 rules to keep track of, and it looks like, again, I have space to write it below. Okay? The very first rule says if you have a vertex that has degree 2, well, since you have to reach that vertex and get a cycle, so I should actually include here, this is specifically for a Hamilton cycle. Not a cycle, a circuit. So if the vertex has degree 2, both of the edges that are incident to the vertex are going to be included in the circuit because you have to include the vertex in the circuit. Okay? So that's an automatic. Now, rule 2. No proper subcircuit can be formed when building the Hamilton circuit. What does this mean? This means you're not allowed to go and visit a vertex you've already been at. So if you're forced to use an edge that closes your circuit too early, or you start getting into like what was perfectly fine in the Euler Cycles where we could visit a vertex more than once. If that happens, you've picked the wrong edges or the wrong vertices in the wrong order, or if this is forced and there's no way around it, no Hamilton circuit exists. And lastly, third rule says once a Hamilton circuit uses 2 edges that are incident to a single vertex, then all of the other remaining edges that are incident to that vertex are not going to be edges that we're going to travel over. Why? Because that's going to force us to then it's going to make it so that you won't visit that vertex a second time is what this does. So all of these rules are really sort of held together all at once. So let us look at a little example where we start applying these rules. And I'm going to start off with a basic example that we've actually already looked at. So suppose you have this graph right here, that same bow tie graph that we've had before. And we already said that we know that there's no Hamilton circuit. We've already talked about that. We were able to find a Hamilton path, but not a Hamilton circuit. So what do you guys think? And actually, you know what? I'll throw this to you guys. Do you think, or can you find, which rule, if any, this graph would violate if you're trying to find the Hamilton circuit? Okay? And I went ahead and I activated this question for you guys so you can actually vote, all of you guys, on which, if any, of these rules you think might be violated. Okay? And while you guys are thinking about that, I am going to go and change my pen to a highlighter so we can see this. A little easier, that is. Now, it turns out these three rules are ones that are typically used to determine whether the Hamilton circuit exists or doesn't exist. So if you think it doesn't exist, typically have violated one or more of those rules. It's typically what happens. All right, it looks like the majority of you guys have been putting in guesses at this point. I know it's not everybody yet, but go ahead, make a guess, see what you think might happen, and I'll start putting in marks, assuming that the rules all work. Okay? So if you put in marks, assuming that all the rules work, if you look at rule 1, it says any vertex that has degree 2, both of those edges that are incident to that vertex have to be included in the circuit. So we'll go ahead and put in both of these edges. So A was degree 2, so we would need to include both the edge AB and the edge AE in that circuit. Now, E also has degree 2, so we'd include both the edge AE, which we already decided we wanted to include, but now we add in the new edge EB. Vertex B is not degree 2, so we're going to ignore him as we look at rule 1. And in terms of right here, vertex C and D, they're also both degree 2, so we'd need to include the edges that are incident to both of those guys, both of those vertices. So if we apply rule 1, and what we would need is we would need edges, well, I don't want to list all those edges. Edges marked with purple. So that takes care of rule 1, and that's all rule 1 does. Now, if we then look at rule 2, what does rule 2 say? Rule 2 says you can't have formed any proper subcircuit. So if we actually went ahead and extended these original edges, oh, I have a different color, didn't mean to do that. If we go ahead and extend those markings to include the full edge, notice what happens on these first 3 edges that we included. What just happened? Anybody notice what happened with that purple writing? As I start to do the same thing on the other side. Yeah. So this is what's known as a subcircuit. It may not be the circuit that we were thinking of. If we were going to start at A, but notice it is actually forming a little subcircuit. It is forming where you can go all the way around and reach wherever you start, depending on which, and it doesn't matter which vertex you started with, you can get all the way back around. But what happened, you didn't actually get to all the vertices. So that's what we can call a subcircuit. So that means this guy here is actually violated by our subcircuit that we formed. Now I'll just start with A for our subcircuit. Our subcircuit was A E, B, or if you prefer A, B, E back to A. Okay. Now, it turns out that we also violated Rule 3, but as soon as you violate even one of the rules, you stop, you say, hey, no Hamilton circuit exists because at least one of the rules is violated. Now, quick check, anybody spot where Rule 3 is violated? Yeah, so Rule 3 says you're not allowed to use essentially more than 2 edges that are incident to any vertex. And here, if we actually threw in all these edges, you would get 4 edges incident to B, and that's not allowed. So obviously, we're going to end here because we're out of time. I've got 2 more examples in this particular section for section 2.2. So on Monday, we'll talk more. If you have any questions about the midterm, we'll also we'll finish up this section, and then we'll start in on section 2.3. But that does mean that the homework for section 2.2 will get moved back. And yes, there should already be one up, but it's not due until Monday in terms of the quiz. Although, I might need to send you an announcement about something in the future. I haven't decided whether it's going to happen or not over the weekend. Yeah, something. No, I need to change a setting on one of your past quizzes, and I got to decide how I'm going to handle that since I did change the setting. All right, well, if you guys have any other questions, I'll hang out here for a few minutes, but I don't have anything more for you guys today. That's it. We're done.